Okay, welcome to a new chapter, lesson 2.1. We are going to talk about graphs and all the different concepts of a graph. I've written out a lot of graphs and definitions, so please pause, take notes, and if you have any questions, let me know. But let's start today on an informal definition on continuity. Continuity is if you can sketch a graph without lifting your pencil, then your graph is continuous, okay? Now, that means there are times where graphs are not going to be continuous, so if I go to try to draw this, I would have to lift my pencil to draw the rest. Same thing at this asymptote. If I go to try to draw this side, my pen would be going up for infinity. I would have to hop on over to then draw this part. So first part of your homework is going to say, okay, determine some intervals of continuity. Now, intervals of continuity are always on the x-axis. Don't look at the y-axis. Look at the x-axis. So here you have a parabola. So we're looking to see if I were to draw this, I have beautiful continuity the whole time. And again, don't forget the parabola doesn't go straight up. It keeps getting open, more and more open. So along the x-axis, along the domain, what would be really the domain of this graph? It would be from negative infinity to infinity. That's the interval of continuity. Now this one looks like a line, but it has this hole in the middle of it, a point, a hole which will happen. So that means from negative infinity all the way up to where on the x-axis, right here at 3. So from negative infinity to 3, I can draw my pencil. And then I can draw my pencil after 3. So I don't want to be on the point 3. So I say united 3 to infinity. If you get an asymptote, it's the same thing. You would say, okay, I don't have to pick up my pencil. I can draw my graph all the way up until this asymptote, which is at 2. So from negative infinity to 2, united with, and then I would do this side, which would be from 2 to infinity. So there are your quick and easy view of intervals of continuity, again, on the x-axis, okay? Now let's talk about a function. Where is it increasing or decreasing? Please, please, please write this down. It's like you read a book. You read a book from left to right. You're reading this right here, left to right. That's the same for a graph. So if right now I put my pencil on the leftmost part and I start to draw it, even though the arrow is pointing up, I am going down, okay? So I am decreasing. And then I start to draw it again after this hole in the graph, and I'm increasing up until about here. And then what happens after that? Oh, I got to go down again. I'm decreasing. And then something changes in the graph right about here, and I don't seem to be increasing or decreasing. I seem to be staying constant. Okay, so now let's write these as intervals. Just, again, along the x-axis. Don't worry about the y-axis. So I am decreasing from along the x-axis. Even though this is up, I'd be at negative infinity. Remember, the x-axis, negative infinity is your lowest number. Until where on the x-axis? Right here, right at negative 2. And it's open. Then I am increasing. From where? From about 2, negative 2, excuse me, until about here, which is 1 on the x-axis. Then I decrease again. So you could actually write united, but I was running out of room, so I'm just going to write it again down here. From 1 to about, I kind of think I shifted that. I think I meant to put it at 3. And then I am constant from 3. Actually, I can close that bracket because that is a closed dot. From 3 to infinity. Okay? So Again, very similar to intervals for continuity. It's along the x-axis. On x-axis. That's how you look at your intervals. Okay, so now we're going to talk about parent functions, and you really need to know these parent functions, be familiar with them. You should be familiar with them. Let's start with the constant function, y equals 2, or f of x equals 2, or f of x equals a number. And we know that hoi over nox, hoi, if it is a y equals, then it is a horizontal line right there. Okay, so if whatever it says right here, f of x equals pi, it would be a horizontal line at pi. What's the domain? How wide is this picture? Well, this is going from negative infinity to infinity. The range, however, is what are your y values? They're always going to be 2. So that's how you would write that. The identity function is another parent function. The identity function goes right through 0, 0. It goes up 1 over 1, up 1 over 1. The domain, how wide is this picture getting? It's getting pretty big, negative infinity to infinity. The range along the y-axis is also negative infinity to infinity. Again, pause this so you can copy these down. Squaring and cubing functions. So x squared is your parabola. Goes through point 0, 0. And then it's at 1, 1, negative 1, 1. And what's the domain? How wide is this picture getting? So this, again, is, even though it looks like it's just going up straight, it's getting wider. So it's going from negative infinity to infinity. The range, how tall is this graph? Well, I don't have any graph right here below 0. So it would start at 0 and it would go up to infinity on the y-axis. The cubing function starts down, curves in the middle, and goes back up. Okay. Now, again, even though these look pretty straight on the graph, they are continually curving and getting wider and wider and wider and wider. So the domain here would be negative infinity to infinity. And the range, obviously, they keep going up and down. So negative infinity to infinity. Okay, 2 more here, the square root function and the cube root function. So the square root function doesn't have any numbers past 0. Remember, you can't take the square root of negative 1. So it actually goes like that. And it shoots off. It rises slowly, but it does rise. Okay, you take the square root of 3, square root of 4. It'll keep rising. So my domain is actually, I can take the square root of 0. So 0 is in the domain. That's why I'm closing the bracket. But anything before 0 is not. And then all the way to infinity. And the range, again, even though it looks like it's leveling off, it's not. You're going to be able to have y values out for infinity. So it also would be 0 to infinity. The cube root function actually looks like, and again, you could always plot these on your calculator. And I want to just go over how to do cube root again. You go math, cube root, which is number 4, x, and hit zoom 6. And you can see it's similar to the cube, except kind of flipped or turned. So it goes like that. Okay. So how wide is this getting? Negative infinity to infinity. What's its range? And it looks, you're like looking at this, you're like, well, it looks like it's only between 1 and negative 1. Now remember, I can change my window and this would still be in the graph. This is going to keep getting wider and wider and taller and taller, and as it goes on and on and on. So negative infinity to infinity. And that's, again, because you can take the cube root of even negative numbers. So these are some of your parent functions. Oh, got one more. Forgot. The absolute value function, one of my favorite ones. So absolute value, remember, if you take the absolute value of any number, it's positive. So if x was positive, it would be remaining positive. But if x was negative and you took the absolute value, they would also be positive. Okay, so it makes this V shape. And for those who don't know where this is, if you go to Math Num Abs, if you ever want to graph it in your calculator. So let's just do that real quick. If I go to Math, go over to the word num, and then the first thing that comes up, abs, the newer calculators actually put the 2 bars there. And you put an X. And zoom 6. And you'll see it will graph that V shape for you. Okay, but just so you know, this is called a piecewise function, which we'll get to very shortly. But what is the domain? How wide is this thing getting? It's getting pretty big, negative infinity to infinity. The range, however, similar to the parabola, it only goes from 0 on up. Okay, now, types of symmetry. There are 3 types of symmetry, and 2 of them are really the more important ones that we use. So there is what's called y-axis symmetry, and I'm going to put this into our calculator so you can see it real quick. This is x to the 4th minus 3x squared minus 8. And see, it kind of makes this W. Yeah, I'm a little off. I can go further, but it will go like this. And y-axis symmetry, if you can see, it means it can flip over the y-axis, that this half looks like this half if you cut it right down at the y-axis, okay? But another analytical way of doing it would be f of negative x equals the f of x, or when you plug in a negative x, you get out the original function. So let me show you that right over here. If I were to plug in a negative x into this equation right here, so this would be negative x to the 4th minus 3 times negative x squared minus 8. If you take a negative number and you raise it to the 4th, doesn't it come out to be positive? So this would be x to the 4th minus 3. Same thing here. If you square it, it comes out to be positive minus 8. Oh, isn't that what the original function is? That's the original function. So that's how you know it has y-axis symmetry. So 2 ways. You can look at the graph, plug in negative x, and get out the original function. Write that down. Let's look at x-axis symmetry. So x-axis symmetry is if you plug in a negative y. Seems weird. Seems backwards, but that's what it is. If you want y-axis symmetry, you plug in a negative x. If you want x-axis, you plug in a negative y. So if you plug in a negative y, you get out the original function. And, one way to tell, we'll do this analytically, x plus negative y squared equals 2. So x plus, again, you're squaring the y. That would be y squared equals 2. Oh, it's the original function. If you were to graph this right here, you may remember this. Solve for y squared equals 2 minus x, and then take a square root. When you take a square root, you actually have a positive and a negative of that side. So what would happen is if you were to, let's say, just type this in the calculator, you would have to write the square root of 2 minus x. Ooh, so many layers here. Move it down. And then the negative square root you would actually have to put into the y2. And what it'll do, there you go. There's that square root function. It's just flipped over. But this is actually 1. Even though they're 2 different colors, this is 1 function. So it actually looks like this. But you can see it's flipping over the x-axis. This one was flipping over the y. This half looked like this half across the y. This half looks like this half across the x. Okay, and last symmetry is what's called origin symmetry. And what this one is if you plug in a negative x into the function, you would get out the opposite sign of the function, or the negative of the function. So again, let me show you that over here by hand. So if I plug in negative x, I get negative x cubed minus 4 times negative x. Well, negative x cubed is still negative. A negative times a negative times a negative is still negative. Minus 4 times negative x actually becomes plus 4x. So now let's compare these two. These are opposite signs. Both of them are opposite signs. So that means we got out the opposite of the original function. So it must have had origin symmetry. Now, what is origin symmetry? Let me just plot this for you in the calculator. X cubed minus 4x. Give my calculator a moment. Takes a while. There we go. Okay, so origin is really cool. It's as if you put your pen right here at the origin and you turn it upside down. Does that graph look exactly like this graph? Did anything shift? It looks exactly the same, right? That's what origin symmetry is. You don't want anything shifting. You want to be able to turn this paper upside down, keep your pen right here. Sorry, I've got too many things in my way. And it looks exactly the same. Okay, so this is origin symmetry. Now, these two are the most important, surprisingly enough. Y-axis and origin. Those are really the two that you're really probably going to be focusing on, not necessarily x-axis as much. But try them and you can look in your calculator and see how they are. And the reason why I said origin symmetry and y-axis is so important is because in math we call them even and odd. I don't know why they changed names. I wasn't the one who created the math. I just teach the math. So here's how to remember if a function is even or odd, okay? If it's even, put a little y right there, it has y-axis symmetry. Or, what did we just learn from before? You can plug in a negative x into the function and get out the original function. If it's if it's odd, I'm giving it away. Odd, O, origin. It has origin symmetry. Which means if I plug in a negative x, I get out the negative of the function. So I'm going to teach you a real quick trick way to do this. Instead of graphing on the calculator, some of them you'll have to do on the calculator, but here's an example. This is your last example, by the way, I believe. Yeah. Determine if the functions are even, odd, or neither. So if it's even, all the exponents of x will be even. All the exponents of x are even. Now, what does that mean? So here's 4 even, 2 even. What's the exponent of a number all by itself? Trick question? It's actually x to the 0. And 0 is an even number. If you didn't know that, you should know it. Because you're going by 2's, 0 would be even. So this is an even function. It has y-axis symmetry. And you can double check that again. Punch this in your calculator, yx to the 4th plus 3x squared, ooh, minus 5. And you can just check to see that it's flipping over the y-axis. Yeah, looks parabolic. That side flips over to that side along the y-axis. So if that's the case for even, what do you think the case would be for odd? You guessed it. All the exponents of x would be odd. So let's see right here. This is 3. This is to a 1. We just don't usually write it. So this is odd, which means it has origin symmetry. And again, origin symmetry is where you can flip it upside down and it looks exactly the same. See, this one doesn't have origin symmetry because this is a frown face. This is a happy face. But if you type that in your calculator, which try it, see if it has origin symmetry, flip it upside down. Or what about this one? Let's see. So this has an exponent of 2 and an exponent of 1. Oh, even an odd mix can't happen. So that's a neither. Okay. Last two, what if I get 1 over the absolute value of 3x? Well, what does that make it? Does it make it even? Does it make it odd? Well, again, you have the power. Use your calculator. So let's type this in. 1 divided by, I'll put times, divided by, absolute value is found in math, num, abs. The absolute value of 3x. Let's graph it. Very cool. So kind of looks like this. The calculator breaks it, but is that flipping over the y, or if I turn it upside down, does it look exactly the same? See, that doesn't look like that. Looks like a hole in the ground, whereas this looks like a volcano. So it doesn't have origin, but it does flip over the y. So this is even. And then this one, x cubed plus 2. Oh, yes, I want to show this because everybody always tricks this one up. X cubed plus 2. And just to look quick, see, they'll be like, oh, yeah. Oh, they look the same. They're both doing the same thing. But see how this one is shifted up 2, and then when I move it upside down, it goes down 2. So that is not origin symmetry. This is not the same. How do I also know the other trick way? This was x to the 0. This is odd. This is even. So this is neither. All right. Hopefully that helped you out with tonight's homework.